Welcome to BK'sTechStack. Today, we're unlocking the secrets behind advanced generative AI, exploring the models and architectures that are defining the future. This is where innovation truly begins. Traditionally, sequence processing relied on models that struggled with long texts, creating an information bottleneck where early context was often lost. They also processed information sequentially, which was a huge performance constraint. The deeper insight is how these limitations pushed us toward a revolutionary change. The solution? Attention. Imagine giving the model a spotlight that can highlight exactly what's relevant in the input at any given moment, rather than forcing it to remember everything. This mechanism provides dynamic relevance, making information bottlenecks a thing of the past. Watch how this shapes what comes next. At its core, attention works by assigning contextual weights. Think of it like a smart filter. For every piece of output, the model decides which parts of the input are most important, assigns them higher weights, and then combines them into a focused context vector. This allows for a much richer, dynamic understanding.
Now, let's refine this further with self-attention. This isn't just about focusing on an input for an output. It's about each part of the input sequence understanding itself in relation to every other part. This internal focus is key to grasping subtle contextual nuances and truly revolutionizing language understanding.
The core of self-attention revolves around three conceptual vectors: query, key, and value, or QKV. Think of it like searching a database. Your query is what you're looking for, keys are the indexed attributes of available data, and values are the actual data you retrieve. The dot product helps determine the relevance. This is the foundation for deeper contextual understanding. Self-attention's power truly shines in contextual understanding. Take the word apple. Its meaning changes depending on the sentence. Self-attention dynamically crafts an embedding for apple that reflects whether it's a juicy fruit or a tech giant. This allows the model to capture complex semantic connections across long sequences, making its understanding incredibly rich. Here's the mathematical heart of self-attention, the scaled dot product formula. It calculates attention by first taking the dot product of the query and key matrices, scaling it to prevent issues with large dimensions, and then applying a softmax to get normalized weights. These weights then multiply the value vectors, summing up to give us that context-aware output. This is where self-attention truly revolutionized AI. By allowing parallel processing, it leaves RNNs behind in terms of speed. More importantly, it directly addresses long-range dependencies, ensuring information from the beginning of a text can easily influence the end. This efficiency is what makes self-attention the cornerstone of modern AI architectures. One self-attention mechanism is good, but multiple are even better. Multi-head attention is like having several experts analyzing the same data, each from a unique perspective. One head might focus on grammar, another on meaning, and so on. By combining these diverse insights, the model forms an incredibly rich and nuanced understanding. So, how does multi-head attention actually work? The input is first split and processed by each head independently, allowing for diverse feature extraction. Then, these individual insights are stitched back together, creating a robust, unified representation. This capability allows the model to understand the context and ambiguity in language more effectively. And that's why understanding this matters going forward. All these concepts culminate in the transformer architecture. It's a groundbreaking encoder-decoder structure that abandons traditional recurrence, relying solely on attention. This design choice, combined with positional encodings, allows for massive parallelization and a global understanding of sequences. The transformer is built from several key components. Beyond multi-head self-attention, we have feed-forward networks for nonlinear transformations, layer normalization for stable training, and residual connections to ensure deep models can learn effectively. Each piece plays a critical role in the model's robustness and performance. Transformers have fundamentally reshaped natural language processing, especially in text generation. They don't just string words together, they weave narratives with deep contextual coherence, predicting the next word with incredible accuracy based on the entire preceding sequence. This predictive power is what enables the magic of modern LLMs. Let's trace the path of text generation with a transformer. It starts with tokenization and embedding, then positional encoding injects sequence order. The self-attention mechanism then works its magic to build contextual understanding, followed by iterative contextual encoding and decoding to produce the final coherent output. Here's where this leads beyond text: image generation. Transformers view images as sequences of pixels, using self-attention to understand how every part relates to every other part. This global perspective, a significant departure from traditional convolutional networks, allows them to synthesize incredibly coherent and imaginative visuals directly from text. Transformers aren't just theoretical constructs. They have immense practical applications right now. From summarizing complex medical records to powering intelligent recommendation engines and offering real-time sentiment analysis in financial trading, their impact is broad and transformative. This is why understanding their architecture matters. Let's look at some leading transformer models. DALL-E showcases the creative power of AI, generating stunning images from text. Then there's the GPT series, which with its decoder-only architecture has become the backbone of advanced text generation and conversational AI, producing remarkably human-like content. Continuing our exploration of leading models, we have Llama, a versatile transformer from Meta AI, adaptable for a wide range of NLP tasks. Then there's BERT from Google, which introduced bidirectional processing. Its ability to look at words from both ends of a sentence fundamentally changed how AI understands context and ambiguity. So, what are our key takeaways? Attention is critical for dynamic context. Self-attention empowers internal relationships, and multi-head attention offers diverse insights. This entire framework forms the transformer architecture, the very foundation of modern generative AI. Keep exploring. The future is exciting.